fractions look like A over B. In other words, there's a number divided by another number or value, and you can see kind of the divide sign defining the fraction. A fraction is made up of a numerator and a denominator. The numerator is what we call the part, and the denominator is the whole. So I might say that my whole has 5 pieces to it, so 5 pieces make up my whole. If I have all 5 of the 5 pieces, I have the entire object. If I have none of the 5 pieces, I have 0. And if I have 0, I have 5 over 0, that is undefined. I can't have 5 of no pieces if there are no pieces to have. Equivalent fractions are fractions that are equal. For example, 1/2 is equal to 2/4. Well, how did I move from 1/2 to 2/4? If we look at this diagram, 1/2, I'm going to shade that in. If I look at a second diagram that looks like 2/4, my whole now is not made up of 2 pieces, but of 4 pieces. And if I shade in 2 of the 4 pieces, you can see that this colored shading is exactly the same amount. To move from 2 to 4, I multiplied by 2 in the denominator, and I also multiplied by 2 in the denominator. 1 times 2 is 2, 2 times 2 is 4. Now, how is this legal in mathematics? This value, 2 divided by 2 is defined above, 5 divided by 5 is equal to 1. All I did was multiply by a 1 that looks different than a 1. It's 2 divided by 2. Let's try a third fraction that is even equivalent to 1/2. 1/2. So let's get our 1/2. What if I was to divide this into 8 pieces, shade in 1/2, and that's equal to 4 are shaded, 1, 2, 3, 4. 4 are shaded out of the total 1, 2, 3, 4, 5, 6, 7, 8. Those two fractions are equal as well. 2 times 4 is 8. 1 times 4 is 4. So again, I multiplied by this value 4 over 4, which is equivalent to 1. So there's a pattern that's happening. If I want to find equivalent fractions, suppose I have 3/4. If I multiply it by a 1, I get a new fraction. However, the area shaded is equivalent. 3/4 is equivalent to 6/8. I don't always have to use 2 over 2. If I took 3/4 and multiplied by a 1 that looked like 5 over 5. Again, I'm just multiplying by 1, so I'm kind of enlarging both by the same amount, and I get 15 over 20. So these two fractions are what we would call equivalent. Now, oftentimes, we start with this larger fraction, like the 6/8. We might start with this, and we would like to go backwards because we like things in reduced form or as simple a number as possible. So looking at 8/12, and I want to reduce that. One way of reducing is just to see if each number can be divided by 2. Notice I'm multiplying by 2. I'm going backwards now and reducing it, not enlarging it, and dividing by 2. 8 divided by 2 is 4. 12 divided by 2 is 6. So 8/12 is equal to 4/6. I can continue with the 4/6. I can divide by 2 again. And remember, what you do to the numerator, you must also do to the denominator. 4 divided by 2 is 2. 6 divided by 2 is 3. So 8/12 in its simplest form is 2/3. I could have right away maybe noticed that 4 goes into each one of these numbers evenly, meaning no remainder. 8 divided by 4 is 2. 12 divided by 4 is 3. So 2/3 in one step versus 2 steps. So we want to look for the greatest value that divides into these two numbers, the numerator and the denominator. So when I look at 6 and 9, I see that 3 divides into 6 and 3 divides into 9. 6 divided by 3 is 2 in the numerator. Denominator, 9 divided by 3 is 3. And in the last problem, 12/27. In this problem, I also see a 3 for each value. 12 divided by 3 is 4. 27 divided by 3 is 9. Looking at 4/9, I would like to take half. 4 divided by 2 is 2, but 9 divided by 2 is not what we call an integer value, so I must leave it.